But atmospheric complexity isn't the only natural system that behaves far differently than scientists once predicted. Ocean current predictability. Ocean currents shape global navigation and climate predictions through patterns that seem remarkably consistent. Shipping companies plan routes based on these reliable flows, while meteorologists use current data to forecast weather patterns months in advance. The Gulf Stream carries warm water northward with clockwork precision, while the Antarctic Circumpolar Current circles the southern continent like a massive conveyor belt. But what happens when these supposedly stable systems start behaving erratically? The 2025 Oceanographic studies reveal something alarming about current reliability. Advanced monitoring systems show major current systems developing unprecedented variability in both strength and direction. These changes occur over weeks rather than decades, completely disrupting established forecasting models. Rising sea temperatures alter the density gradients that drive these currents, while melting polar ice changes ocean salinity levels across entire basins. The Gulf Stream shows clear signs of weakening, with flow rates fluctuating unpredictably. Arctic currents shift direction without warning as ice patterns change dramatically. Climate change creates interconnected disruptions that compound current instability. Altered wind patterns modify surface currents, while deep water formation processes slow down in polar regions. Natural climate cycles like El Niño now interact with human-caused changes in ways that make accurate predictions nearly impossible. These dynamic ocean systems represent just one example of how seemingly stable geographical features actually involve far more complexity than simple models suggest. Tectonic plate boundaries. Geological textbooks present tectonic plate boundaries as clean, simple lines separating different plates across Earth's surface. These diagrams make plate boundaries appear like borders on a political map, precise divisions that clearly separate one plate from another. But what happens when geologists examine these boundaries using advanced monitoring equipment? The 2025 Tectonic research reveals something that completely changes this neat picture. Modern GPS measurements, seismic monitoring systems, and detailed geological mapping show that plate boundaries aren't simple lines at all. Instead, they represent complex zones spanning hundreds of kilometers where multiple fault systems interact simultaneously. The Ring of Fire around the Pacific Ocean perfectly demonstrates this complexity. Rather than a single fault line, it consists of multiple overlapping plates including the Pacific, Philippine, and Nazca plates all converging through different geological processes. These boundary zones contain networks of faults, volcanic chains, and seismic activity that spread across vast areas. This complexity directly influences geological activity patterns. Convergent boundaries create mountain ranges and volcanic eruptions across wide regions rather than along narrow lines. Transform boundaries generate earthquake swarms that affect extensive areas. The distributed nature of tectonic activity makes geological hazard assessment far more complicated than simple boundary line models suggest. These same complexities affect the most basic tools we use to navigate and map our planet. Geographic coordinate systems. Latitude and longitude measurements depend on systems that constantly shift beneath our feet. Most people assume geographic coordinates represent fixed, unchanging points that remain accurate forever. After all, latitude and longitude seem like basic mathematical measurements that should stay constant. If a location sits at 40.7128 degrees north, 74.0060 degrees west, that's where it stays permanently, right? But what happens when you examine how coordinate systems actually work in practice? The 2025 Datum System updates reveal something that completely challenges this assumption. Different reference systems like the World Geodetic System 1984 and the North American Datum of 1983 assign slightly different coordinates to identical locations. These variations seem small, but accumulate into significant positioning errors across large distances. Tectonic plate movement creates even bigger problems for coordinate accuracy. Plates shift several centimeters annually, gradually moving entire landmasses away from their recorded positions. GPS systems rely on WGS-84, which requires regular updates to account for these continental movements. Without constant recalibration, navigation systems would become increasingly inaccurate over time. Modern mapping technologies must handle these coordinate variations through sophisticated software that automatically adjusts for different datum systems and plate movements. Surveyors working on major construction projects face costly errors when coordinate systems don't match properly. Even the most fundamental tools we use to locate ourselves on Earth involve far more complexity than anyone realizes. Geography continues evolving as rapidly as the technology we use to study it. These 50 myths reveal how 2025 satellite measurements, GPS tracking, and advanced monitoring systems expose decades of outdated information that millions still believe. The facts you learned in school represent snapshots from decades past, not current reality. Continental drift continues happening right now. Ocean currents behave unpredictably. Even basic coordinates shift due to tectonic movement. These discoveries emerge constantly as measurement techniques improve and new data becomes available. These misconceptions shape how we view climate change, resource distribution, and global relationships. When geographic understanding stays frozen in time, we miss critical changes happening around us. The world keeps moving, and our knowledge must move with it.